Hey, everybody. Say, is this the very last lecture, or it's my last lecture? Do you have any more lectures coming up?
Yes.
Okay. So I still owe you a couple write-ups. I will send them to you. I get insanely busy, but next week, well, I said this before, next week I should be able to start at least. I looked at how complicated the write-ups are, and we covered a lot of material. So it'll take me a little while, but I'll definitely have them on the website guaranteed within 2 weeks. So I say, never trust any predictions by a professor. We always underestimate how much work we have. Okay, people are joining at a high rate. So let me start. So we've been talking about decision making under time pressure, and to really understand how to analyze those mathematically, we need a little primer in reinforcement learning. So reinforcement learning is learning just from rewards. Get reinforced or not reinforced. And it's really how we learn high level cognitive things. It's and possibly even how we learn motor control, how to walk and run and play sports. It's probably not so responsible for learning things like, tuning our visual system or having hearing things better or language, but for a lot of things, very relevant paradigm. And mathematically, it's been simplified to states, actions, and rewards. So there are states, actions, and rewards. And we always draw, when we draw these things, we draw really simple state spaces. The reason reinforcement learning is hard is because, well, one of the reasons is because state spaces tend to be really big. So at any particular time, first of all, there are lots of things you can do. You can pay attention, not pay attention, you can leave the room, you can call your friend. And also, and the state is really the state of the world. Your environment, it's what I'm saying, it's it's internal state, how hungry you are, things you need to do. So states are really, really big and typically exponentially big, and that's what makes it hard. Also, the states, we're going to assume for a while the states are observed, so you all know what state you're in. In fact, that's not true. There's always a lot of uncertainty about what's going on. Okay, so this is a really simple world with 4 states, and when you make transitions, I'm going to make the transitions a little bit easier this time. There's really simple transitions. And when you transit, you get different rewards. So going from 1 to 2, you get reward of 100. It could be yuan, it could be gold bars, so it doesn't really matter. From 1 to 3, you get 1,000. From 2 to 3, 5,000. And then for the last one, you get, let's say, 500. Okay. And this reward structure is what makes reinforcement learning and what makes decision making hard. So we're going to start in state 1, and you get your choice, state 2 or state 3. If you don't look ahead, if you're very greedy or short-sighted, this looks like a better transition. You get 1,000, right? However, had you gone this way and waited a little while, you got 100 there and 5,000, and you would have been a lot. You would have gotten much bigger reward. And so, what you want to do? So your goal. So find policy that maximizes the sum of future rewards, okay? And it's a future there that make things so complicated. So the rewards we write as it's a V. So in general, we write the value of a state. And so the value of a state, so this is sort of the key thing that we introduce in reinforcement learning is V equals, let's get rid of this thing. So this is really, how do we solve this problem? So how do we solve this problem? Or how do we achieve our goal of maximizing rewards? And one way to do it is sort of two main ones, but one is V compute value, and value would just use V for value of each state. Under some policy. Okay, we're introducing two more new things, value, which we call V, and policy. And the policy is just an action in each state. Each state. Okay. And let's say, so we really only have one decision to make. So let's say pi 1, policy, we use pi's for policy. Pi 1 means, not a very good one, looks like a 2. So policy 1 is go from state 1 to state 2, and policy 2 is to go from state 1 to state 3. And really that's our only decision, because once we get here, we have to go to state 3 and have to get to state 4. And once we get here, we have to go to state 4. And now what we can do is write down the value of state 1 under policy 1. And that is equal to, let's write this so it's pretty, so we get value. So pi 1 means the value of state 1 under this policy. So equals R, reward we get when we go from 1 to 2, plus reward we get when we go from 2 to 3, plus reward we get from 3 to 4. And the value of policy 2 under policy 2 of state 1. I'm not sure policy 1, policy 2 of state 1 equals R 1 to 3 plus R 3 to 4. Okay, so that's pretty simple, but it suggests an algorithm, because R, if you'll notice, this quantity here, so R 2 to 3 is just the value of state 3, right? The value of state 3 is reward you get going from here to here and here to here, okay? And this quantity here is the value of state, the value of state 2. Value of state 2, the value of state 3. Okay. So basically these value updates under a policy are recursive, right? So sort of in general, like what, it's very, very loosely, you can actually write the value of a state equals the reward you get from going to S to S prime plus the value of S prime. Okay. And this is a policy, right? So we put a policy here. I mean, we can kind of sometimes drop the policy as long as it's understood. And the policy in this case, so pi says action, so action of state, state 1 is go to state 2. I'll go to state S prime, okay? So this is action. Okay. So I'm going to introduce probabilistic policies in just a second, but we can think about this policy first. And so this is, I've done stuff that's sort of insanely simple, right? I started with this picture. We saw, okay, the greedy policy is not a good one. We want to do this policy. We wrote down some obvious equations. The value of a state is some of the rewards you get. Value and the different policy, you get some of different rewards. We realized these were recursive, right? If you start here, the value of this state is because it's the sum of rewards. The value of a state is basically the reward you get plus the value of the next state. And it's because it has a sum of the rewards there. Yeah, for those of you who know a little reinforcement learning, we sometimes put discounting in here. I'm going to ignore discounting for now. And discounting means future rewards are not worth as much as current rewards, but let's ignore that. It's more realistic, but we don't need it. Okay. So just having this structure give automatic this recursive relationship. This recursion relationship is actually super powerful because, here's how you can, so how to solve an RL task. And there are lots of algorithms. This is a huge field. There are probably hundreds of algorithms, but it is a really simple one. So, and this is if you know all your states. And also, I mean, honestly, you don't even have to know all your states. Let's get rid of that because in some sense, you don't really need that. But you need to know something about the state. So you initialize V of S equals the value of each state. And so you could have V of S equals 0. So that's one option. And the nice thing about this is you don't have to know anything about the states, and what you can do is wander around state space, and every time and so initially, if you've never seen a state before, it's value is 0. But we're going to update these values. So initialize initial. Okay, and then choose a random policy. Pi, which remember pi equals mapping from S to S prime. Okay. So what do we do? So we basically, and then we just wander around the state space. So we start in state S, start in S. In state S, could be any state, you're plunked down in a state. So you get V pi, and then you have V pi of S. You go to state S prime because that's what your policy says. On this policy equals R S to S prime plus V pi of S prime. Okay, and this is so policy tells us so pi maps S to S prime. Okay, so you've chosen a policy. Sometimes some states aren't allowed, so you have to choose a policy that's actually allowed. Go to R S prime. So remember, on a first step, everything's 0, right? So what you're going to find is that V pi of S does not equal R plus V pi of S prime. Okay, you have the wrong values. The predicted value of R, so predicted R reward equals V pi of S minus V pi of S prime. So if all your values were correct, that's what you would get. Now, on average anyway. I mean, rewards can be stochastic, but let's say they're deterministic. That's predicted reward. Actual reward is R. So reward prediction error is equal to what you expect, V pi of S minus V pi of S prime minus R, S to S prime. So this is expected reward, and this is actual. Okay. So let's repeat this. This is incredibly important in reinforcement learning. It's incredibly important in life. So remember, V pi of S equals R S prime plus V pi of S prime, and RPE equals V pi of S minus V of S prime minus R S prime. Okay, so we're going to use that error to update our values, right? If we have the correct values, the reward prediction error is 0. Okay, so if RPE is greater than 0, let's say RPE is less than 0, we're unhappy. So in the brain, this is signaled by a drop in dopamine. Which makes us unhappy. And what we do is we update our values. So V pi of S, so basically V pi of S was too big. Goes to V pi of S minus or plus RPE plus eta times RPE. This is learning rate. Okay. So it makes sense, right? If eta is negative, if RPE is negative, the value drops a little bit, right? This was too big. You overestimated how much value that state has. So if RPE is greater than 0, we're happy. Signaled by, we get a shot of dopamine. And that causes the same update rule, right? Same update rule, but now RPE is positive. Same update rule. Okay. So this is the simplest version of the world. This is what happens, and this is what we thought maybe 30 years ago. As usual, it turns out things are much more complicated. Dopamine is not the only neuromodulator. And there are multiple types of D2 dopamine receptors, and punishment rewards are handled differently. But this is not a bad first order pass of how we learn from rewards. Okay. And so dopamine, of course, is now, I mean, after 500 million years of evolution, the shot of dopamine was makes you happy. So positive reward prediction errors makes you happy. It's not rewards that make you happy. It's unexpected rewards. And that is super, super important if you ever have kids or are dating somebody. So for instance, you should never, never, never take a kid into a candy store and then buy them candy. Because eventually, walking into the candy store, the value of walking into the candy store is they predict the reward. And then so this is walking into the candy store, they get a reward, the value drops, and the reward prediction error is 0. It doesn't make them happy at all, right? It's only unexpected rewards that make kids happy. They adjust to it and they expect candy when you walk in the store, and they whine and cry when they don't get it. Okay, because if they walk in the store and they don't get candy, negative reward prediction error. Okay, so it's really your reward relative to what you expect. Same thing with significant others. Never take somebody into a store and then buy them a gift. Because once they get used to getting gifts inside stores, you get no happiness from it and you get no credit. Okay. Okay. So this is how to update our values. How do we change our policy? So eventually, so you've done this a long time. You wander around state space, you collect rewards, you update values. And this is kind of what you do, right? You learn what actions actually provide value. And then at some point you're in state S, and you go to S prime or S double prime. You have choice of 2 actions, S prime or S double prime. And let's say the value of this state, value of S prime equals 10, and the value of S prime equals double prime equals 20. So the policy in state S, go to state S double prime, okay? Now that seems like a totally reasonable policy, except really these are estimated values. You don't never know for sure exactly what a value is. Often rewards are probabilistic. So typically what you do is you go to state S pi, go to state S double prime, go to state S double prime with probability. In the simplest case, 1 minus epsilon. This is called epsilon greedy. And go to state S prime. S prime with probability. Okay, so you sort of hedge your bet. There's an explore-exploit trade-off, right? In the past, this has been a valuable step. It's got higher value, but maybe, first of all, the world is stochastic. Maybe things will change. Maybe you've misestimated its value, and so you want. So this is the exploit, and this is the explore. Okay, and you always want to do both. And the explore-exploit trade-off is pretty non-trivial. Okay. So before we get back to decision making, I want to introduce one more thing, and that's probabilistic rewards. So in fact, if you're in state S1, let's say, you might be sometimes an action doesn't take you necessarily to you don't necessarily have total control over what states you do. Okay, so it could be under policy 1, P of state 2 given state 1 equals 0.6, and P of state 3 given state 1 equals 0.4. Okay, under policy 2, P of state 2 given state 1 equals 0.2, and P of state 3 given state 1 equals 0.8. Okay. Now, why might you not have control? Why why do you not always have control of what state you do? And that's because the world's stochastic. So let's take the train example. This is a train example. So train example. So policy one is leave for train station at 8 o'clock. So P of getting on train equals, let's say 0.9, and P of missing train, because train times are somewhat stochastic, depending on, it's worse in some countries than others, equals. In Switzerland, you know exactly when they're going to come. In my country, it's a little more variable. So, you leave at 8 o'clock, the odds are you'll make the train, but you might miss it, right? And policy two, so these are different states if you miss it versus make it. Leave for train at 8:05. Okay, and that means P of getting on train equals 0.4, and P of missing train equals 0.6. Okay, so depending on your policy, whether it's leave at 8 o'clock or leave at 8:05, gives you, you're in states with different probabilities. So state 2 would be making the train, state 3 would be not, or so on. Okay, so the world is stochastic. So we've actually, so let me actually write down one equation, and then we'll sort of review what we did. So V of a particular state under some policy equals a sum on S prime, P of S going to S prime. Again, this is under some policy, different policy to give it different probabilities. And the reward you collect going from S to S prime, plus the value of under this policy of state S prime. And you'll notice the reward transition don't depend on the reward you get in these transitions in classic RL don't depend on the policy, but the probability of making particular state transitions and the value of these state transitions does depend on policy. Okay, and so this is a pretty sophisticated equation. This is Bellman's equation. Bellman's equations. It's a linear equation. So basically, to make this complicated, you go, what you put in here is Bellman's equation sometimes means well, I won't say it. You can put a max, the value at the optimal policy is the max over all possible actions of the right-hand side, but that's kind of a detail, okay? So, this is a sophisticated equation that came from a very simple idea. And the very simple idea is that you have this recursive relationship. The value of pi is about sum of a bunch of future rewards that can go way into the future, but it's really the value of this reward plus the value of the next state. Okay. So for instance, just to try this point home, the value under value of state one under policy one, the value of state one equals reward going from 1 to 2. Actually, sorry. With probability 0.6, it equals reward going from state 1 to 2 plus the value of state 2, again under policy 1, plus 0.4, the reward you get from going to 1 to 3, plus the value under policy 1 of state 3. Okay. In policy 1, we've only told you about the state 1 transitions, but policy 1 is going to have all the state transitions. Okay. And that's just what we wrote down. Okay, so we're almost ready to do decision making. In fact, we can actually go now to our decision making task. And try to use these ideas to give us an optimal policy. Okay. And we're going to go to, so this is, we're going to go back to the coin flip one. We're also going to talk about the random dot kinematogram, but the setup is before. We have 2 coins. So coin 1, C1 equals coin 1. And the probability of heads equals P1, and C2 equals coin 2. The probability of heads equals P2. Okay. And so basically what we get is a sequence of heads and tails. Okay, so, you know, heads, tails, tails, heads, tails, heads, heads, heads. So let's say, you know, eventually, and our policy is decide when to exit. Okay. And now we have to ask, what do we want to maximize? So we could, so what do we maximize? So we could maximize reward, you know, per task. Okay. And that's a horribly bad idea. It's a bad idea because we wait forever. Okay. So let's say, you know, let's say example. So example, P1 equals 0.8. P2 equals 0.2. So P1 is more likely. So what we're looking for is, if we get more heads or tails, you know, if we, and let's say we flipped 100 coins, we got about 80 heads and 20 tails. It's possible that's a fluke, right? There's a very small probability if we guess heads, we'd be wrong. It's exponentially small, but it's still possible. So we go to 1,000 coin flips, 1,000,000 coin flips. No matter how many coin flips we got, there's a small chance it's just a random fluctuation and we're getting the wrong answer. Okay. So this is a bad idea. So what's much more sensible, maximize reward per unit time. Per unit time. So rho equals R bar under some policy divided by T bar under some policy, rho of pi. So choose pi policy. So policy is just, that's our policy, which is when do we stop? Choose pi to maximize rho pi. Okay. Okay, so this is, it should at this point actually be kind of mysterious how we're going to connect this to reinforcement learning. Okay. We have, you know, the language looks the same. we have a policy, which is, when do we stop collecting coins and make a decision? We have something that rewards, we have average time it takes, which is average number of trials. So let's be clear about this. So T bar average number of coin flips. Before we make a decision. Okay, but it's not really obvious what the state space is. Okay, and in fact, the state space in the worst case scenario is horribly big. So in some sense, the problem really here in this situation is to figure out what the state space is. Okay, we have the setup. We want to turn this into RL problems so we can use RL machinery. And the RL machinery we're going to use is this machinery here. We're going to write down this recursive relationship and use that to find the optimal policy. The policy to maximize rewards. Okay. Okay. So what are we going to do? So sort of, I'm going to start with a worst case state space. State space. So we always start on S naught. Okay. So this is, and there's some value to S naught. So we can take that, the actual value doesn't matter, right? So we'll take value of S naught equal to 0. So if you notice in this recursive relationship here, if we added, V pi, actually, let's write it down. Let's write it here. Oops. So if you look here, so the value at some pi is really reward we collect, but the next value. If you added 10 to that value, every value would change nothing, right? It's only differences in value that matter. And so we're going to let V at S0 equal 0. Okay. And now we get information from the environment. We either get a heads or a tails. And sort of worst case scenario, heads puts us up here. Tails puts us down here. Right. So these are now different states. Okay. This is, this is a state, that's a state. Because a different state of the world, we've gotten different information. And one thing that's interesting about that is the state depends on the past information, which is kind of standard. This is H, this is T. Okay. And the problem, of course, is state space is getting bigger and bigger. 20 coin flips are now to the 20th over 1 million states. Okay. And then, but let's say that, at here, our policy is to in each state, our policy is to keep going or make a decision. And let's say that our policy was, if we hit this state, we go back. Collect reward. Which we'll call just R here. It's R that depends on the state. We'll call it R. Actually, R, we can give it a name. It's an R of HTH, right? Sequence heads, tails, heads. Collect reward, and we go back. And if we wrote down our standard RL updates, so standard RL update, we'd write V of S naught equals reward we collected, R plus V of S naught. Actually, let's be clear about R in this case. R of HTH plus V of S naught. Okay, so this is, of course, highly problematic, right? Because V of S naught is V of S naught is if this R is positive, these are supposed to be the same. The value here is always 0, right? And so there's actually a sort of a cheap trick we can do. We can write instead, so this is a cheap trick. There's actually, mathematically, you can show this is the right thing to do. So V of S0 is really, we're going to make it R. So R, and sort of in general, the reward we get minus rho T, where rho is R bar over T bar equals average reward rate. Okay. Okay, so this is kind of, plus V of S9. So now if we do this on average, if we actually, did this thing on, if we ran a value, this value iteration of what I described before, every time we go through this, we look at, so the expected reward is, the expected value of R minus rho T is V of S0 minus this V of S0 should be 0. On average, that's going to be the case. Kind of average R is going to be R bar and average T is going to be T bar. Okay. So what this comes down to is sort of a two-step process. So what we want to maximize is R minus rho T with rho equals R bar over T bar, right? And we can, keep track of rewards to compute this. Keep track of old rewards. Old rewards and times. To compute this, and then optimize this quantity. Okay. In fact, you can, there are lots of ways to keep track of rho, okay? And so this is kind of non-trivial, right? This sort of, what I've told you so far, we should do this, but this doesn't make any sense because the value would just grow. In some sense, so what you want to do is subtract off the average reward per time times time, so these things stay 0. So on average, V of S0, we can go around this loop many times, and V of S0 is going to be 0. Okay, so that gives us now a way of solving these problems. We can write the value of a state. We still haven't told you what a state is yet. The value of a state at time t. So far, the state is going to be one of these things in these coin flips. There can be exponentially many of them, but we're going to soon collapse that state down to something much smaller. Okay, the value of a state equals now depends on what you do. So this is our policy. The policy is the sum on S prime P of S prime given you're in state T times V, times V of S prime, the usual thing, right? It's your usual update rule. There's no, so this is actually if we wait. So we don't make a decision, we gather more information, and then we want to subtract off minus rho. Because if you subtract off minus rho, remember T is really just a number of time steps. So if we do this, that will reduce the value by, this is sort of average reward per time step. You subtract that off, so this on 0 on average, or rho on average. And then over here, it's just R bar of ST, R of ST, R of ST, this is expected reward, R of ST, if we choose a coin. Okay. And again, I still haven't told you what a state was. In fact, in worst case scenario, our state is this sort of exponentially large state space. But let's now see that we can actually reduce the state space massively. And so you'll notice that the key quantity we need, so to compute, certainly to compute the average reward in the state space, we need P of C1 given data. Data, remember, is our head, tails, tails, head sequence. Okay, because we know the probability of a coin, we can pick the one with higher probability. And to compute P of S prime, P of S prime given ST. So for that, what this really is P of X given data, some sequence H, T, T, H, T, H. Okay, this is data, and this is heads or tails. Okay, so the probability of heads or tails depends on which coin we get. So we can write this as P of X given C1 times P of C1 given data plus P of X given C2, P of C2 given data. Okay, and you'll notice that in all cases, if we know P of C1 given data down here, if we know P of C1 given data, we know P of C2 given data because there are only two coins. If we know these two quantities, that's enough for us to compute the transition probabilities and update and compute the average reward. So really, so the question is, what state will allow us to compute this? Okay, so we can go to the next page. I'll do this and then we'll stop and take a break. P of C1 given data equals P of data given C1, P of C1 over P of data. That's just Bayes' theorem. And this is equal to P of data given C1, P of C1, that's prior, over P of data given C1, P of C1, plus P of data given C2, P of C2. So all we knew is P of data given C1. And let's say data, is heads, tails, tails, heads, tails. So this equals P of H given C1, P of T given C1, P of T given C1, P of H given C1, P of T given C1. Okay, so equals in general, the product tau equals 1 to T for n time step T, P of X given C1, and X is H or T. And so this, of course, is equal to P of H given C1 times the number of heads times P of tails given C1 times number of tails. Okay, and I think, where are our coins? Our coins are here. Yeah. So P of heads given C1 is P1, P of heads given tails given C1 is 1 minus P1. So this is equals P1 to the NH, 1 minus P1 to the number of tails. and P of data given C2 is equal to P2 to the NH 1 minus P2 to the NT. Okay. And now we see that this quantity here, we can write, actually I'm gonna write it on the next page. So what we want is this quantity, P of C1 given data, okay? And the reason we need that is because if we have P of C1 given data, we can compute both the average reward, with the expected reward, and these transition probabilities. Okay. So let's go to the next page, the last thing I write down. So P of C1 given data is equal to P1 to the number of heads. Oops. 1 minus P1 number of tails, P of C1 over P1 to the NH, 1 minus P1 to the NT, P of C1 plus P2 to the NH, 1 minus P2 number of tails times P of C2. And we can write this in a very nice form. 1 over, let's divide through by the numerator, 1 plus P2 over P1 to the NH, 1 minus P2 over 1 minus P1 to the NT, okay? And we can take this quantity to be our state space. So we started off having a state space that potentially was exponentially large. It turns out that if we just want to know these probabilities, all we need is a single quantity, okay? And in fact, we'll usually take a log of this and we write the state, which is a function of NH and NL, is equal to NH and NH log P2 over P1 plus NT log 1 minus P2 over 1 minus P1. And that's our states. And it's a single number. And you can plot it on the line. So we start here at 0. Every time we get heads, we jump up by log P2 over P1. So this is heads, heads, heads. And if we get tails, we jump down by log 1 minus P2 over 1 minus P1. One is positive, the other one has to be negative, okay? Okay, and this is actually what we saw in last lectures. But now we've derived, this is really the relevant state space, because if we know P of coin 1 given data, we know everything. Right here, yep. P of coin 1 given data, we know how to compute the average reward and how to compute the transition probabilities. Okay, because if we know this, we know the probability it's coin 1, we know the probability it's coin 1, we know the probability of heads, probability of coin 2, again, we know probability of heads. Okay. So let's stop here and take a 5-minute break. And then I will continue and talk about the case when there's more than 2 coins and then the random dot kinematogram. And then possibly we'll look at, well, we'll just keep going. Okay, I'm gonna record, save the photos just in case. And I'll come back in 5 minutes. And again, if you have any questions, feel free to ask. Sorry, I stepped out for a second. So in the off chance somebody had a question, they should ask it again. Okay, let's start up again. Unfortunately, as usual, I have to, oops. Oh, my video's gone. Stop share, start share again. Okay. So that was the case of one coin. What happens if we have more than one coin? Oh, so by the way, I mean, let me finish off that diagram I made. Our state space S, state space. It's continuous, right? So we jump backwards, we jump up. And basically our policy is when to exit. Policy is when to exit. Basically just bounds. Bounds. And we often draw this as flat bounds. So we put on this axis, number of heads log P2 over P1 minus number of tails log 1 minus P1 over 1 minus P2, 3 minus sign here on this axis. We start here at 0 and we sort of wander around. And so our policy is these bounds. Okay, so we go up, we go down. The steps are now different, but eventually we hit a bound and, you know, we say, okay, it's coin 2 or coin 1. Okay, so that's all pretty straightforward. This is a 2-coin picture. And as we'll see, there's something very special about 2 coins. Okay, we're going to make things harder and harder and harder. We're going to now consider the case of n coins. And n coins may seem kind of weird, but eventually when we talk about the random dot, go back to the random dot kinematogram, we're going to see that's an issue. So again, what's our state space look like? All we need is a probability of coin I given data, right? So I guess, so the reward structure, let's say +1 for guessing. So we want to actually, for guessing, you know, it's, we'll divide its reward. So there's lots of reward structures we could do, but if we want to make this binary, reward, group coins into, well, group coins into groups. Let's say, so group 1, P, so basically n coins, so we need, actually, let's write that down. So coin I, so P of heads equals PI. So group 1, you know, PI is greater than or equal to some cutoff, P naught. And group 2, PI is less than P naught. And the reward is, so +10 if we guess which group it's in. So minus 10 if we guess incorrectly. Okay, that's the usual setup. So what we need for this is P of CI given data. Okay, and if we know that, we can compute transition probabilities. So P of X given data is equal to sum on I of P of X given that it's coin I times the probability it's coin I given data. All right, and again, X is, so X equals H or T. Okay, these are supposed to be brackets. Okay, and if we know PCI, we can compute, P, it's in group 1, equals a sum over all PIs greater than or equal to P naught. Of P of CI given data. So we can compute everything we can do. We can run the reinforcement learning problem. And the question is now, what's our state? Okay. And again, we just need P of CI given data, so we can write that down easily. So P of CI given data. Again, Bayes' theorem, most useful thing in the world. P of data given CI, P of CI over the sum on J, let's write this down, divided by P of data, okay? Usual Bayes' theorem, but P of data, as usual, is the sum on J equals 1 to N, P of data given CJ, P of CJ. Okay. And finally, P of data given CJ equals the product from tau equals 1 to T, P of X given CJ. And this, of course, is equal to P of PJ. This is a probability of heads given coin J to the number of heads times 1 minus PJ, probability of tails and tails. Okay. So what we have is that P of CI given data is equal to PI to the number of heads, 1 minus PI to the number of tails times P of coin I divided by the sum on J, PJ to the number of heads, 1 minus PJ to the number of tails, P of CJ. Okay. So this is a kind of complicated function, but what's clear is that the function only of NH and NT. If we know the number of heads and number of tails, we can compute these probabilities for any I. So we'll call this Fi. And so we can't do the old trick. Our old trick was divide by numerator, right? And that just gave us a single function. Now we have two functions, a function of two variables. So what this tells us, though, is that our state space, so remember, sort of worst case state space. So worst case state space was this exponentially big. Exponentially large. Okay. Actual state space is two numbers. Okay. And we can take them to be NH, oops, number of heads, number of tails, or which is more common, number of heads minus number of tails, and number of heads plus number of tails equals, we'll call it capital N because I use N for number of coins. And that means that our RL problem our policy takes place in this space, NH minus NL minus NT. And on this axis, we have N, total number of heads. And we start here, we just go up and down, right? And our policy is some kind of boundary in here, but it should be collapsing. I mean, that's intuitively clear, but showing that it's not totally trivial, but it's not that hard to convince yourself. So optimal policy is collapsing bound. Okay. And you can find that using any reinforcement learning algorithm. Okay. So it's kind of nice. We started off not knowing what the the state space was. We said, okay, exponentially large state space will work, but actually we don't need exponentially large state space. We just need to know the number of heads and number of tails, which is sort of convenient as a difference and a sum. Okay. Optimal policy is collapsing bound. Remember, the reason it collapses is because sometimes there are lots of coins. Okay. There are N coins, coin I probably have heads as PI. So, and really what we want to know is probably above or below some cutoff P naught. So if we get ahead, and so let's say P naught's 0.5, if we pull a coin for which the probability of heads is high, like 0.9, we'll very quickly realize it's bigger than 0.5. If we get a coin whose probability of heads is 0.55, it'll take a lot of flips before we realize. We might even get a probability of heads, a coin whose probability of heads is exactly 0.5, in which case it takes an infinite number of flips to distinguish these two. And that's why we have collapsing bounds, right? If we get a coin with probability near this point, let's say 0.5, it goes forever without going anywhere. And we might as well eventually say, okay, we're not going to get it right anyway. We might as well guess. Okay, and these bounds, I believe the bounds actually go like that if you wait long enough. Okay, and it's kind of interesting. These bounds can even, under some circumstances, it's possible for the bounds to go up first. They can have all sorts of shapes. And if you make the problem more complicated, they can have lots and lots and lots of shapes. Okay. So this is fairly sophisticated machinery we're using, right? This is kind of all very non-trivial. And now I'm going to make it even worse by considering going back to the random dot kinematogram, which we talked about last time, which has its own set of problems. Okay. So we'll go back to the random dot kinematogram. Not really sure how to spell it. It's known as RDK in this business. So remember what it was? It was moving dots on a screen, and these arrows represent velocity. They move in different directions, and they flicker on and off. So it's kind of hard to tell. So C equals coherence equals fraction equals fraction of dots moving to right. To the right. Okay. And our data is P of xt given C. And this is a variable. This is a noisy estimate of C. So C goes from -1 to 1. And so if this is actually our true value, this is a 1. What happened? -1 to +1. So true value, then this is P of xt given C. Okay, it's some distribution. I'm not going to say what it is yet. Eventually we will. So no estimate of C. And what our data is well, this is one data point. One data point. Sorry. So that we have P of x given C is this is our model. Our model. And the data is x1, x2, xt. So our data is these independent observations of these noisy estimates of C. There's some time between x1 and x2, which is usually about 100 milliseconds in simulations, but it doesn't really matter, okay? And what we want to do, so remember, as usual, all we need, and so, and again, what do we need to estimate rewards and transition probabilities? So to estimate, and usually what we're going to do is we're going to collect data for a while and eventually stop, okay? So to estimate, and what we want to know, so goal, determine whether C is positive or negative. Negative. And when C is 0, of course, that's actually impossible. Okay. So, okay, so basically, probability of C greater than 0 is the integral from 0 to 1 dc P of C given data. So we should write this as probability of P of C greater than 0 given data. Okay, that's that integral. And then transition probability. So P of xt given data equals the integral dc P of xt given C. So remember, P of xt given C, this is part of our model. So this is assumed known. Okay. So that's known, and then P of C given data. So once again, if we know P of C given data, we know everything. Okay. And we can easily write down what P of C given data is. So P of C given data, except it's now an integral, equals P of data given C, P of C over integral P of over P of data. Bayes' theorem again. My favorite theorem. And that is equal to P of data given C, P of C, divided by integral dC prime, P of data given C prime, P of C prime. Okay. It's the usual thing, but again, all we need is P of data given C. Okay. And that's easy as well. P of data given C, the thing we need, equals product tau equals 1 to t, P of xt given C. Okay. And log P of data given C, always take logs when you're doing probability, equals the sum tau equals 1 to t log P of xt given C. Okay. So everything looks fine, right? We could accumulate log P and that's our data, right? But there's a problem. There are an uncountably infinite number of C's. So if this is an arbitrary distribution, doing as you were with reinforcement learning or during reinforcement learning, it's really hard. We have a continuous, in fact, uncountably continuous state space. So the state, so in this case, the state S is equal to sum S at time t, this, write it like this. So S at time t of C equals the sum tau equals 1 to t of log P of x tau given C. I'm guessing I've been writing stuff wrong. Okay, possibly not. I may have written t in the sums instead of tau. Okay. And so we have there in uncountably infinite number of C's. Number of C's. Okay. And so our state space is now, it started off in the coins, it was really small, two discrete variables. Now it's sort of uncountably infinitely large. It's a continuous state space. So reinforcement learning, it's continuous state space crossed with this addition thing, right? So you can't even draw it. It's a function. So state space is map from one function to another. So in general, this is just an intractably hard problem. But the fix, so exponential family distributions. So the sort of the theory of exponential family distributions, which I know way too little about, is absolutely beautiful. But the truth of the matter is almost every distribution you write down is in the exponential family. So basically, if we can write down a sensible distribution, P of xt given C, then our life becomes much easier. So let's take an example Gaussian, which is in the exponential family. So P of xt given C is equal to e to the minus xt minus C squared over 2 sigma squared divided by square root of 2 pi sigma squared. Okay, so log P of xt given C is equal to minus xt squared over 2 sigma squared plus C over 2 sigma squared xt minus 1 over 2 sigma squared minus 1/2 log 2 pi sigma squared. Okay, and now the sum, so st of C is a sum of this, right? So it's basically going to isolate to sum of the terms. There's a C over 2 sigma squared. The sum tau equals 1 to t xt plus, or so minus 1 over 2 sigma squared minus 1/2 log 2 pi sigma squared times t, and then minus the sum tau equals 1 to t of x tau squared over 2 sigma squared. Okay, so if let's take the case where sigma squared is independent of C. So sigma squared doesn't depend on C. So the only C dependent, so all you need to compute xt is basically you need 2 quantities to fill in the distribution. So if you know this, so you need this and sorry, this is a t. Okay, so if you know that and that, so this is enough to reconstruct the distribution. Distribution, right? So this is the case where C sigma squared is known and doesn't depend on C. Okay. And so you can see why, right? Let's go back to our state space. I hope this works out because I didn't check this. ST equals the sum tau equals 1 to t log p of x tau given c equals actually I just wrote it down, right? Yeah. So we'll just call this so we'll write it here. So ST equals, let me go back to this. C over 2 sigma squared times the sum on tau of xt. Actually, I'm going to skip this. Come back to here. It actually takes a little thinking, but if you know these 2 quantities, the sum on t of xt and the sum on total time, you can actually, it's enough to reconstruct this. And partly because if you exponentiate that, you get actually a normalizable distribution. So it takes some thinking. But the point is, though, that what happens is when you're all done, is a state space. On this axis, we put the sum on t, or tau equals 1 to t of xt on this axis. And this axis, we put time. And then we just put in some bounds. Again, collapsing bounds. So you start here, and you integrate, and you go up and down, and you run around, and then you make a decision, okay? So the policy bounds in evidence / T space. So this is evidence, okay? So it's all very intuitive. And so if, you should try to convince yourself of this as well, if sigma squared is unknown, you need to keep track of actually, I think it is sigma squared depends on C. Need to keep track of some tau equals 1 to t of xt squared. And it makes sense because you now have to infer the variance, right? You know what the variance is. You have to keep track of this as well. And then sort of your boundary becomes a lot more, your policy becomes a lot more complicated because it takes place in 3-dimensional space. The sum of the squares, the sum and time, and how the circuitry that your brain uses to do that is unknown. So we can write down circuitry that does this. When this is taken into account, it's much less clear. Okay, so I have about 5 minutes. I think the thing to do is to try to summarize what we've done, which is not going to be easy because we've actually done a lot. But what was the problem we faced? The problem is, so we're getting evidence about 2 options. And our problem is to decide when to stop gathering evidence and make a decision. Okay, and you know the solution is to sort of integrate on this, put on this axis evidence, and this axis time, and add some sort of bounds. Okay, which usually collapse. And they usually collapse because some of the evidence is informative and some isn't. And so the reason we want to collapse because we might be in a regime in a trial with very little evidence. The chance of us getting it right are small. Okay, and so this is sort of an intuitively appealing picture. Is what's in all literature, and what we did is put some teeth into this. Okay, and so to figure out what the evidence is, You know, and how to compute bounds, which I didn't tell you, but we could compute them by any reinforcement learning algorithm, compute bounds. So we turn to RL. Reinforcement learning. Often known as RL. And so the idea here really is so the key equation is value at time, you know, time t, a value of a state. We get this very sort of intuitive but powerful equals R S to S prime. This is a deterministic case plus the value of state prime. It's undiscounted exponential. You know, as a note, sometimes people put, well, I'm going to ignore discounted RL. And this gave us, you know, this led to very powerful algorithms. So there's a policy here, right? So you find a pi, given pi, you find all the values. This led to powerful algorithms. And told us what the state space was. Okay. We didn't solve Bellman's equations, but we sort of I gave an intuitive method. We have this value iteration. But RL is a huge, huge field. And there's lots of, I mean, you can't really talk about it in half a lecture. It needs lots and lots of lectures. Okay, so I got to go now. Can't hang around because I actually have to go to a meeting. I hope you enjoyed my lectures. I never quite know what pace to do. I think I get feedback, so feedback would be very useful. And there are lots of write-ups. I'll also put a bunch of reinforcement learning write-ups on the webpage. I'm not sure they're exactly appropriate, but they kind of give a flavor. And you can look into these a little more deeply. Okay, thanks very much. As usual, things will appear on the website. It'll probably take a couple hours because I won't be back for a while. But thanks very much. And I'll see you later.
Thank you, Professor.
Sure.
Thank you for great work.
Okay.
So maybe 1 or 2 weeks later, you will give us a brief summary about your course, about this part of your course.
I'm trying to do it less than 2 weeks, but certainly within 2 weeks, I'll give you a summary. Yeah.
You said next week you would be very busy.
Yeah, well, I'd be kind of busy.
Okay.
I'm less busy than this week. But I'm going to start writing. It's going to take a while to write, so I'll hopefully start next week. And I'll email you as soon as things appear on the website. I'll do the first part and then the second part, then a little bit of reinforcement learning.
Okay, great.
Okay, thank you.
Yeah. Any problem?
Sorry, what?
Any questions?
Any questions?
No question.
Okay. Okay.
Okay.
Bye.
Yeah, thank you. Thank you again. Bye.
Bye.